Almost always what we're talking about is the semiconductor silicon. Later on we'll talk about why silicon is especially a good thing. Silicon is in group 4 of the periodic table. If you remember back from chemistry somewhere, that means that it has 4 electrons in its outer shell, the so-called valence electrons. Remember, 8 is the magic number for most elements when they want to form bonds to form a chemical structure. And silicon forms the diamond structure in which every atom makes 4 covalent bonds with 4 adjacent ones. So we have 4 electrons in the outer shell, and then we share electrons from 4 adjacent atoms. Forms a very stable structure similar to the structure of diamond. It's a crystal, ideally a very uniform crystal with tetrahedral structure. Okay, group 4 of the periodic table. Just in terms of the density of the atoms, it's somewhere between 10 to the 22nd atoms per cubic centimeter and 10 to the 23rd atoms per cubic centimeter. That's just how many there are in crystalline silicon, just to give you a frame of reference. Now, the critical thing here is that almost all of the electrons that are involved in those covalent bonds are active and are used in forming the structure. And therefore, they're not free to just move around in response to an electric field. As you raise the temperature, vibrations happen. Raising temperature is really the average energy of the molecules, average energy in the crystal. And so as we begin to raise the temperature, occasionally an electron will be shaken free of a bond, leaving behind a positively charged hole. The concentration of such free electrons and the holes that are left behind is relatively small. But those electrons, if there's an electric field, if they're not involved in bonding, then if there's an electric field, they can move. And that's very important. There's not very many of them. Silicon forms a so-called semiconductor. It has some free electrons, but not many. The concentration of electrons of pure silicon is called the intrinsic concentration. So this is actually, in practice, we don't very often have so-called intrinsic semiconductors where they're pure, no impurities. But if we did, the concentration would be somewhere on the order of 1 times 10 to the 10th free electrons per cubic centimeter. For reasons known only to the history, we use the CGS, the old CGS system when we talk about device physics. Instead of the MKS meters, kilograms and stuff, we use centimeters and that other stuff. This is all in the notes. So the number is 10 to the 10th or 10 to the 11th. Depends on who wrote the book. It's so dependent on temperature and the assumptions of the physical modeling that nobody knows exactly what the right number is. It's probably not worth arguing about, although it shows up in all the equations that we use. This one is at the temperature being 300 K. So the higher up in temperature you go, the more likely it is that we're going to have created free electrons and left behind the so-called holes. All right? So this is the concentration for pure silicon. The reason we don't spend much time actually talking about pure silicon is even a very, very small concentration of any kind of impurities tends to overwhelm the concentration that we would have had in pure silicon. So typically in silicon, we intentionally add impurities of either 2 types in order to control the concentration of the electrons or holes that are in the material. All right? So that kind of material is so-called doped or extrinsic. Doped. So doped implies that we intentionally add something to it, impurities, to control the concentration. If we use the doping, then we find that the dopants and the impurities have a very large effect on the behavior of the system. Let's go over to the board next door because I've already kind of made a mess there. So if we have so-called N-type semiconductor, then we will add impurities which are called donors. And donors come from group 5 of the periodic table. And group 5 of the periodic table is 5 because it has 5 electrons in its outer shell. If you substitute in the crystal for a piece of silicon an impurity from group 5, it might be phosphorus or arsenic are the main ones that are used. We're not going to need to know much about that, but phosphorus or, I guess it's AS, right? Arsenic, all right? Phosphorus or arsenic. And they are in group 5. It is very easy for the extra electron, the 5th electron, is very easy to give up. When I say it's very easy for it to be freed, it isn't really needed for bonding. And so if there's any energy at all, if we're at any temperature significantly above 0, absolute 0, then there's enough energy to shake that electron free. The crystal lattice is pretty much satisfied. There's a negatively charged electron that's just available to move in response to the flow of to an electric field. All right? And so pretty much however many donors we've put in, the number of donors is capital N sub D, and it might be somewhere between, it's probably less than about 10 to the 20th carriers per cubic centimeter. This is a very heavy doping. And if it's less than about 10 to the 15th or so, you can't really control it very well. So intentional doping is usually within those 5 orders of magnitude. All right? So intentional levels of this are 10 to the 15th, which is 1 part in about 10 to the 8th, or about 10 to the 20th, which is about something on the order of 1 part in 1,000. All right? It would be a very, very heavy doping. So it doesn't take a very high concentration of these impurities to completely control the electron concentration. So we're going to have the concentration of electrons in this type of N-type material. Concentration is N, and it is almost entirely equal to the donor concentration. What that means is that at any reasonable temperature, with a very high probability, as many dopant atoms as we've added, we have that many electrons. The number of electrons N in this material is essentially equal to however many dopants we have. All right? And so the donor atom is fixed in place, and it becomes ionized. So the donor atom itself becomes ionized, and that's important because the atom, of course, is fixed in place. It doesn't move. There's an electric field. It just sits there. There's a positive charge left on it because it gave away its electron. So electrostatically, it has a charge, and it's a positive charge. It's a positive ion stuck in the crystal, substituting for an electron. Okay? We'll come back and say a few more things, but that's the general idea of N-type material. Electrons is pretty easy to get the idea that there's free electrons available to move around in the crystal. As it's going to turn out, the more electrons we have, the easier, the more current we can get. So we can control the conductivity of the material by how many N-type dopants we put in, how many electrons we have in the material. Okay? The other side, and I'll go over to board 2 just to illustrate, is P-type material. Same thing. And in P-type, we have things that are so-called acceptors, which are a dopant atom, and they come from group 3 of the periodic table. All right, so they have 3 electrons in their outer shell. In this case, we would really like to have 4 electrons, valence electrons per atom for bonding purposes, for chemical purposes. And so it is very easy for an electron from somewhere to come and ionize these acceptors. So the ionized acceptor is fixed and has a negative charge. 1 negative charge per acceptor. All right. By the way, acceptor, the main acceptor is boron. There are other things in group 3 that can work, but that's the most common acceptor is boron. All right, and it's in group 3. So ionized acceptor has a negative charge, and it stays fixed. And the absence of an electron, I'm going to write that somehow, but it's a little difficult concept. The absence of an electron in the crystal at some point in the crystal is like a particle. I'll say like a particle. We treat it as a particle. And that particle is positively charged. It's mobile, and it's called a hole. A hole. I can't write. All right. So what's in some sense really happening is that there are electrons that are maybe in a response to a field. The electrons are moving one way and they're filling the holes, but the place where there is an absence of an electron moves the other direction. If there's a positive electric field, a particle, which we can think of as an actual particle just like an electron, moves as a positively charged particle. And if that seems a little mysterious, don't worry about it. We'll talk about it some other time. The concentration of holes in this material, concentration of holes in this type of material is approximately, which is P, and it's almost exactly equal to the number of acceptors. Again, these are equal because if you have acceptors in this material, the fact is, at any reasonable temperature, the electrons are going to find their way into those holes and leave, electrons will find their way into the lattice and leave behind the positively charged holes. So in semiconductors, we may have P-type material where we have an excess of acceptors, and they're fixed in position with negative charge, and we'll have lots of holes that are available to move in response to an electric field. Moving to the next board, N-type material, we'll have an excess of donors, and the concentration of donors will be approximately equal to the concentration of electrons. The donor atoms are negatively charged ions because they are positively charged because they've given up their electrons. The negatively charged electrons are available to conduct current. Okay, so that's the real basic concepts that we're going to be dealing with. Now, back in chemistry class, there's a couple ways of explaining this, none of which are completely clear, I don't think, but it's okay. We just need some equations and just to feel a little bit of comfort. So, in chemistry class, they used to talk about electronegativity, and it had something to do with how strongly an element wanted to grab a hold of electrons, right, or get rid of electrons. And so there was sort of an order based on the physical properties of different materials that said this one really wants to give up electrons and this one really wants to get them. So there's this concept of potential. And it kind of applies to the different materials that we have here, except for we can control the local potential, the tendency of these materials to hold or give up electrons based on the doping levels that we just had. So let me just define this without any further argument. For N-type material, I guess I'll go to this board. For N-type material, all this is true, but I'm going to erase it because I want to use this piece of board. So for N-type material, there is a built-in potential of some sort, which is phi, and it's N because it's N-type material. And it's defined as, and I'll tell you what these things are in just a second, Kt over Q, we'll say that about 50 times every day, Kt over Q, times the natural log function of the ratio of the actual electron concentration to the intrinsic concentration, which was just a constant that we had. All right? And typically, in N-type material, N would be greater than the intrinsic concentration. K is Boltzmann's constant, T is absolute temperature, and Q is the charge on electrons. Kt over Q, for our purposes, is almost always more important than any of the individual terms. So I'll ask you to memorize that Kt over Q is about 0.026 volts at room temperature. Now, right off the bat, we don't necessarily know what temperature it is on a given day. So this number is not always 0.026. It's not that important that we know the exact details or many decimal places of this. It's about 1/40th of a volt, and it depends in proportion to absolute temperature. Okay? Sometimes called the thermal voltage, and we'll use this all the time. It's thermal because of the T. The thermal voltage. And we'll use that every day, over and over. So you might as well get used to it. All right? So typical values of the built-in potential depend entirely on the values of the doping. If I tell you that we're at 300 degrees, and I tell you that Ni is about 10 to the 10th, 10 to the 11th or somewhere, and then we look at reasonable values for the value of the doping, so N is usually Nd, and I said Nd is typically between 10 to the 15th per cubic centimeter and maybe 10 to the 20th or so per cubic centimeter. This thing, the built-in potential will tend to be from somewhere like 0.2 of a volt up to about 0.5 volt. So that's the ballpark that we're talking about. And I don't know the numbers, you can plug them in yourself. So that is about maybe 0.2 volts or something up to about phi sub n equals about, say, 0.5 volts or so. Okay? So that's the ballpark of these built-in voltages that we're talking about. And that is some sort of a potential associated with just the material, and it's controlled by temperature and the doping level. For p-type material, there's a minus sign. I always mess up minus signs, but it's in the notes, so I know it must be right. So here, it's given with a minus sign, Ni, and it's given by this. And again, the typical dopant levels, P would normally be set by the acceptor concentration, and again, it would be somewhere in the ballpark of 10 to the 15th up to 10 to the 20th or so, 20th, 21st, something like that. And these are built-in potentials. And that may or may not mean anything to you, and it's okay, but it's going to mean something specific in just a few minutes. So these things by themselves are really, like anything that's called potential, you normally think about the difference in potential between two places. And when we do that, this will all make more sense, I think. All right, page 2, lecture 2, the p-n junction. At some point, we're going to have materials, when they're useful typically because in one part of the material we have p-type, and in some other part of the material we have n-type. The place where we go from p-type to n-type is the junction. That's the definition, when we switch from p-type to n-type. By the way, if we have some of each, if we have Na minus Nd, and if Na is greater than Nd, then we'll call it p-type. And if Nd is greater than Na, we'll call it n-type, whichever is greater. When we have both, that's called compensated, but I think it's probably worth pointing out. All right, so let's go over to that piece of board. We'll remember these equations, these formulas. We'll go over to board 4. Now, the p-n junction is really, like I say, the most important and most fundamental thing in device physics for our purposes. On the p-type side, so we have somewhere over here, I'm going to use this picture later. So I got p-type over on this side, and I got n-type over here. Over here, there's lots of holes. Somewhere there's a junction in between. Any situation where you have a whole lot more of something in one place, and they're free to go wherever they want, and you have more in one place than you have in another, then they're going to want to diffuse away. That's just a simple fact. If things are moving around and there's lots of them over here and nothing else changes, then there's eventually going to be a tendency for them to move to where there's not so many of them. If you open up a bottle of perfume, the molecules will eventually move away from where there was lots of them until it fills the whole room. That's by the process of diffusion. And it's got simple differential equation, which we'll show and solve, but that's the main thing. Over on the the right-hand side, we have a lot of electrons, and if nothing else were going on, they would tend to diffuse away from where they're in the lots of them towards places where there's not as many of them. All right? And if nothing else were going along, these things would eventually just fill the material, and there would be lots of electrons and lots of holes everywhere if nothing else was going on. They would diffuse until it's totally boring. Okay? As you might guess, other things happen. So what happens in practice is that we get a current due to diffusion of the majority carriers on this side, and we get a current, a motion due to diffusion of electrons from this side. And what's going to tend to happen when we are all said and done is that there is going to be a region formed in the middle where we're close to this junction. This is the junction where it switches from p-type to n-type. And eventually we're going to get an area where most of the holes have moved away from this side and most of the electrons have moved to that side. The fact that these are charged means that that's not all that happens. Okay, so we're going to have a balance between two tendencies. The second tendency is, as we begin to move the holes out of one side and the electrons out of the other, we begin to form a region in here where there are relatively few holes and a region here where there are relatively few electrons. And here's the tricky part. When we get to an equilibrium, we're going to get an area that is a so-called depletion region or depletion layer. N and P are relatively small. So over here, P is less than NA, and over here, N is less than ND. And what happens here is, because P is less than NA, there are charges left behind. Remember we said that in p-type material, this is p-type material, but we have relatively few holes. We still have acceptors. They're fixed in position. And to the left of this dotted line, there are acceptors. They have accepted electrons. They are negatively charged ionized acceptors. So there is charge in this depletion layer on the left-hand side on charged acceptors. Let's assume for the moment that there are Na of them and that they are negatively charged. So there is a charge concentration of negative charge over there, which is minus Q times whatever the concentration of acceptors is. If there was no holes at all in here, and that's what we're going to assume. So I assume that P is really small so that there's lots of charge on fixed acceptors in here, and there's a net charge of minus QNA in every local area of this. Correspondingly, on the right-hand side, the electrons have moved away. Take my word for it for the moment. When we finish the solution, we're going to find that there is a region here of that's depleted of electrons, but left behind are the donors. The donors gave up their electrons, so they're positively charged. Okay? So this is a so-called space charge region. A region of space charge. A space charge region. All right, and we're getting to the main point here. So the fact is, the fact that we have separated charges out in here means that there is an electric field. Whenever you have different concentrations of charges in different positions, you can use Poisson's equation, if you know that, and figure out what the electric field is. If it's a constant amount of charge per position, then we're going to get a field distribution here. I can actually draw these distributions. So let's assume that Na is a constant. This is neutral. There's holes and approximately equal to Na over here. So P is equal to Na. This is neutral, and so there's no space charge. When we get to here, I'm going to assume that we have negative charge, which is proportional to, it's negative, it's proportional to the number of charges times the charge on each one, minus QNA. And over here, I have positively charged, and this is plus Q times the donor concentration. And I'm assuming they're constant, and I'm assuming that this is the shape that they take on, and that turns out to be a pretty good approximation, which is good because it's nice and easy. We can figure out how it works pretty easily. Now this produces an electric field, and me and signs, let me see if I can get the sign right. This particular drawing produces an electric field that would be in this direction. All right, so there's 0. So this is the field. This is the charge density, rho. This is the electric field as a function of position. This is position. This is right at the middle of this junction. So we get a peak electric field here. Now the reason the field is important is that the field is producing a net current in the opposite direction. If we look at what happens, if we put an electron in here, it will tend to move away from the direction that it wanted to diffuse. So, there's an electric field, produces a current, that opposes the diffusion. This is all in the notes, but some people like me to write this stuff down. So if we have this material, there's actually a lot going on. Electrons and holes are being generated. There is a net motion of carriers due to diffusion that is into and across the junction, and there is a net motion of carriers away from the junction due to the electric field. All those things are balanced. There's no net current. The net current is zero. And the net current of electrons is zero, and the net current of holes is zero. So the time we add it all up, everything, all this excitement, averaged out to zero. All right? So you can show that the net amount of current everywhere is zero because the drift field, due to the electric field, is exactly balanced the tendency to diffuse. We can write some equations on that. I'm not sure we need to, but you can figure out everything based on that. Let me go back to my notes. Okay. So actually, if I integrate this potential, integrate the charge using Gauss's law, I can figure out how much this area right here allows me to get the peak field, or I can take this area either one. The two areas are equal. And it turns out that the maximum field, epsilon max right here, is equal to minus Q in A times this distance. X sub P or something, I guess. X sub P. Let me see if I have that right. And I can do a similar thing on the other side. I'm going to come back and finish all those derivations in a minute. I'm probably getting ahead of myself. And there's a 1 over epsilon s here. I'll come back and we'll do these derivations. The net result, though, is if I integrate this thing, the integral of the field is the potential. Okay? Just from definition of potential, I guess it is. I don't ever know. I don't do fields. I just use them. All right? So when we finish all of this, we can figure out that the total charge, when integrated, allows us to get the field. When we integrate this, it allows us to get the potential. And the net potential is equal to the total built-in potential across the junction, which is the thing that's separating these guys. I'm going to go to board 3 and give you the bottom line of this. There is a net built-in potential, which is the difference between the two magnitudes. It's the sum of the two potentials across the two sides. If we go through this, it's KT over Q times the natural log of N, but N is ND, so I'll just put that in there, over NI, minus a minus, let's see, this is minus, minus a minus, so this is plus, KT over Q times the natural log of ND over NI. And using the basic properties of logs, this is the thermal voltage, KT over Q, times the natural log of NA times ND over NI squared. Right? So when we take the sum of the logs, we get to take the log of the product, basic property of logarithms. So this number is somewhere between about half a volt and 1 volt. And it's called the built-in potential. And it is a potential that is fundamentally there. It has to do with the doping, and its function is to support the diffusion current being balanced by this built-in electric field. The diffusion current wanting to cause the carriers to flow towards the junction, the electric field forcing them in the opposite direction. All right? So we can compute all of this if we know the temperature. We have somebody will tell us what Ni is, and somebody will tell us how much Na and Nd is. We can get this. If we don't even know what the built-in potential is, it's probably between 6/10 and 9/10. Just if you don't need to know anything else, you don't even need to know a whole lot to know that the built-in potential at room temperature is going to be in that ballpark. Yes, question? So he wants to know about the graph of the E field. I'm going to redo that graph, and we're going to go through it carefully in just a minute and go through that derivation with a little more slowly. I just wanted to kind of get the basic idea here. All right? So the next things that we can do, and I can do this standing wherever I want, I guess. If I apply an external voltage source such that it's positive on the inside and negative on the P side with a battery or some other voltage source, it will tend to widen the depletion layer. It will tend to increase the field that is separating the carriers, and it will get no net increase in current. That's a so-called reverse bias. If you put positive voltage on the N side and negative voltage on the P side, it will tend to widen the depletion layer, and you won't get much of an increase in current. On the other hand, if you put the voltage source such that it puts additional positive voltage on the P-type material with respect to the N, it will tend to oppose the electric field and leave behind the diffusion currents. It will reduce the tendency of the carriers to be separated, and they will begin to flow across the junction. So if I put so-called forward bias on the junction, diffusion currents will flow, and you can get a very rapid increase in the total amount of current, and we're going to be deriving that and using that formula. So that's the basic operation of the p-n junction diode, which allows current to flow for one polarity of the input of the voltage and tends to reduce the current for voltages applied in the other direction. The question is, what happens if you said somehow exactly neutral silicon on one side and you just had N-type on the other? Yeah, you could still make all this stuff work. It's hard to get really neutral stuff, but theoretically we can certainly do it, and so we can do it. And there's some other combinations that we can do. So we're okay with that. So the first thing I wanted to say is that almost always, for one thing, just as I was saying, it's very hard to get extremely pure silicon because it's just, there's going to be something in there. So somewhere down in the 10 to the 13th is about as low as you can go with the doping. You can't get it truly intrinsic. And second thing is, generally when we have a p-n junction, the way we build it, it's really important that one side is almost always much more heavily doped than the other. And that's very nice because it simplifies the equations a lot. Now I'm getting ready to do some derivations, and I'm going to assume that one side of the p-n junction, that I think I'm going to assume that Na is much greater than Nd. All right? It turns out that in every practical application we will do for the next 2 semesters, that's a perfectly good assumption. All right? And so that's the so-called one-sided junction approximation, and it's just easier to keep track. It's easier to build things where the doping on one side is much heavier than the doping on the other. It simplifies a bunch of equations. The textbook doesn't make that simplification, and it complicates all their equations. All right? So I'm going to do the simpler version. Now we only have 7 minutes left, so that's why I wanted to do it. All right, so I'm going to make a bunch of assumptions. I'm going to take this same picture, but I'm just going to do it a little faster. I'm going to try and do it, and we will be able to get the charge distribution, the field, and the depletion layer, and this applies for either a zero bias junction or a reverse bias junction, and so this is actually extremely useful. All right, so here's a diode of some sort. It's p-type on one side, just like I showed. It's n-type on the other. I'm assuming that the Nd, Na is much greater on this side, is much greater than Nd on the other side. I'm assuming that they're independent of position, so it's constant on each side. It's easy to fix that part. This side we're going to stick with. I'm going to assume that if we have any bias, it's either 0 or it's in the size to be reverse bias, so there's not going to be much current flow. And I'm going to assume that everything else I say is true. All right. If we look at the charge distribution as a function of x, this is x, then what I claim it's going to look like is I'm going to get a narrow depletion layer area over here and a wide one here, and I'll explain why I know that in just a minute. So there's no charge over here because there's holes and acceptors. We get to this point, we've got lots and lots of acceptors, and they're negatively charged. Over here, we've got a lower concentration of donors. Go out a little farther here, and they're positively charged. All right, So this is, as I showed on the previous diagram, minus Q times NA, and this is plus Q times ND, and I claim that and then this is X, let me use whatever I had in here, W, width 2, and this is X equals 0, and this is minus width 2. All right, I have made an important thing when I drew this. I claim that the area of the two charges, of the total charge on each side, is equal to the size of these rectangles, and it's this total charge over here is QND times W2, and this charge is minus QNA times W. This one should have been 1, minus omega 1. And the two charge magnitudes are equal. There's equal charge on either side of the p-n junction. It's a net neutral device. It doesn't just have charge laying around on it. The two charges are equal. If I make the assumption that Na is much greater than Nd, that implies that NaW1 is equal to NdW2. That implies that W1 is much less than W2, and that the total width of the junction is almost entirely into the less heavily doped side. And that's our first big conclusion that we get from understanding how this thing works. There is a depletion layer, but it extends almost entirely into the less heavily doped side. All right? And we're going to say that most of the stuff is controlled by this less heavily doped side. And I say it so many times I want to have something so I don't have to write it down too many times. So the depletion layer extends almost entirely into the less heavily doped side. It's overall neutral, and you could solve for what this is, but what I'm going to do to really simplify this is that the total depletion layer width, which is really W1 plus W2, is the total depletion layer width. All right, just simplifying things. All right, any questions there? So there's almost always a heavily doped side. The depletion layer normally extends most into the less heavily doped side. If I go through now and find the electric field is actually the integral of this, and it therefore is a triangle that has a shape like this. All right, and you can easily show that the field is 1 over epsilon s times the integral of rho dx, and the integral of rho dx is just this area, and so the maximum field is minus 1 over epsilon x times q n a times W1, but I really want to do it over here, so let's do it from this side. It's also true from here, so that is approximately minus 1 over epsilon s times q nd, the doping on the less heavily doped side, times W2, which is approximately W. All right? So that's the field in that direction, and that's just the integral, really, of this rectangle as a function of position. All right? And there's a minus sign in there. Yeah, I don't care about the minus sign, but that's correct. If I integrate this thing one more time, I'm integrating a triangle, and I want to get the potential as a function of position here is what I'm looking for, and it's the negative integral of the field as a function of position, and you can figure out what the total variation of this is by the total area of this triangle. It's minus 1/2 the base, which was Q in, or the width was ND times NA times W. The width was W. And the height of this thing was this. So the minus sign goes away. There's an epsilon s in the denominator. There's a Q. There's an ND. And there's another width. So the width is squared. So the total voltage across this thing, it's a parabola feeding upwards, but then it's a parabola shooting downwards and coming down like that. And this is the potential, and this distance is the built-in potential. And this phi is W squared, the width squared, times Q times ND divided by 2 epsilon S. And that's what I was trying to find. This voltage, if there's no applied voltage, is the voltage across the semiconductor. And so I just took 1/2 the base times the height. This was the height. The base was essentially W, and I plugged it all in. If this is set equal to the built-in potential, which I can compute, one more step, and then that's as far as we're going to be able to go today, I can solve this one for the depletion layer width as a function of everything else in here. And when I do that, I get that the width is equal to the square root of 2 times the permittivity of silicon divided by, which I should have mentioned earlier, QND times the built-in potential. So this is actually the big deal that we have here. We're out of time, and I'm going to start somewhere in this vicinity next time. I'll probably have to go through this over again because we were going so fast. But this allows me to figure out the depletion layer width as a function of the doping and the built-in potential. And the built-in potential came from the doping. It's going to turn out that we can add to the total potential by applying external voltages, reverse bias, and that'll allow us to figure out things like how does the width of the depletion layer change as I apply different reverse biases, and we're going to be in business. So I'm going to probably redo this at the start of class next time, but you should go through this in the textbook. The same thing as in the textbook, except for they didn't make the assumption that NA was always much bigger than ND. So there's a little more complicated, but you can simplify it. All right, well, we're out of time for today. We'll start from here. It's going to turn out that this is a very important result that will get us very close to being ready to start doing real electronics. All right, that's all we have time for today, though.